So let me switch to English. I have the distinct pleasure of introducing our next speaker in the University of Prishtina Math Department seminar series, Vjosa Blakaj from the Technical University of Munich. Vjosa, we're delighted to have you here. You will be speaking about the Quantum Shannon theory, the entropy-constrained sets. As usual, you have around an hour in total we have for this. So I hope that we will start with some more general material and then become more specialized as we go along. So thank you again. It's really a pleasure to have you here and to see you, although from quite a distance. So thank you. The floor is yours.
Thank you. It's a pleasure for me to be here also. Okay. Okay, now I can share my slides. I guess everyone can see them. Maybe someone can comment if you guys can see my slides.
Yeah, we can see your slides.
Ok, se I pata po mdopet do persona 3 erdhen e mu dasht me. Okay. Okay, so it's a pleasure to be here again, and today I will give a brief introduction into quantum Shannon theory, which is basically my field of my doctorate here, and I will focus on entropy-constrained sets. So basically, this part about the entropy-constrained sets is a joint work that I did with my supervisor, Michael Wolf. And the paper is already published in Analyse Henry Poincaré and can be found under this DOI here. So, okay, what is basically quantum theory in general? So quantum theory can be regarded as a general theoretical framework for physical theories, basically. It consists of mathematical core, so of which becomes basically a physical theory when we add a set of correspondence rules which tell us which mathematical objects basically we have to use in different physical situations. So in general, why the word quantum here? So I would say the slight difference from classical information theory to quantum information theory is basically that here in quantum information theory, we learn how information can behave following the rules of quantum mechanics, basically. So in other words, the models which are considered here are formulated with underlying physical theories. And all we learn is basically how we can communicate information and how we can store it. So in quantum data compression or classical data compression, I'll start with that first. What we have is we have a source, which I denote by X. And in classical theory, this is just a random variable, basically, with a specific probability distribution. And here we deliver a message, basically, which is taken from a message space, which I denote by X. And this is fed into an encoder, where it's being compressed, and then this is transmitted into a smaller space, basically. And the idea in the end is to use a decoder to get the information in the end, hopefully with very much accuracy with the initial message that we had. So basically the question in the end is how much or what is the probability of error between the initial message that we had and the last that we get in the end, basically. So in 1948, basically, Claude Shannon had two major questions which were answered in classical theory. So basically, how much can a message be compressed? And the answer can be found in the source coding theorem, which I will not talk about it, but I just wanted to briefly mention. And the second question is, at what rate can we communicate reliably over a noisy channel, basically? And again, the answer is given by the noisy channel coding theorem, but I will not talk about that either. So the thing that I want to mention, which is related with classical data compression, is that the optimal rate at which we can compress information is given by this function here, which is called the Shannon entropy, basically. And it's just the expected value under the measure information. So measure information here is minus log of the probability distribution px. And why is this a good measure for information? So imagine, for example, if we have this, if we deliver a message x, say with very low probability, then the information in the end will be high, because this is also called as a measure of surprise, because we are surprised by the message that we see in the end, because basically the probability of this message was very low in the beginning, and vice versa. So if we have a very high probability that the message will happen, then the measure of information, it will be low, because the surprise will also be low, because we are expecting somehow this information to be delivered in the end. Okay, so before I go to the quantum analog of Shannon's coding theorem, I have to introduce, I think, the bracket notation, because myself, I was not familiar with these before taking courses in mathematical physics, basically. So I assume maybe that the audience here also is not very much familiar with these notations. So if I denote by H Hilbert space, then the elements of this Hilbert space are denoted like this and are known as kets. And if I consider basically the dual of the Hilbert space, then the elements in the dual space are denoted like this. And these are known under the name of bra, basically. When I join this two is the usual inner product, I can say more or less, and it's basically just the bracket of these two elements. Okay, something else so this bracket notation was initiated by Paul Dirac, and the ket bra has to do more with operators, basically. So this is just a function in the Hilbert space H, and it takes an element from the Hilbert space, so say phi, and it's mapped into this quantity here. So my talk will be heavily based maybe upon these notations. So that's why I want to talk about them here first. And also something which is quite important in quantum theory and in my talk is basically operators which are known as density operators. And usually, so in quantum, what quantum theory does, it divides the description of any physical experiment into two parts. So the preparation and the measurement. So the preparation of is usually done by considering the density operators. So these are just bounded operators in the Hilbert space, and this one here is denotes the trace class. This means that these operators have finite trace, and specifically, actually, these have trace one, and they are just positive semi-definite operators. And the other part, maybe I can mention this, of the experiment is based on measurements, but I will not talk about that. And this is done by something which is known as observables. And these are also some specific operators in the end, but I will not mention them in my talk, basically. So now that I gave the introduction of density operators and bras and kets, I can briefly mention Schumacher's compression. So the difference from the Shannon's compression, which was a classical case, is that now as a source, we don't have any more random variables, but we have these density operators, basically. So in the case where we only have basically a ket and a bra attached to it, and these vectors have norm 1, then these are known as pure states. So basically, I mentioned earlier that bras and kets are basically for the Hilbert space and the dual Hilbert space, but if we have only Euclidean spaces, then these can be thought as this one, for example, as a column vector and the bra as a row vector when the entries are conjugated. And when you attach a bra and a cat, basically you get the usual inner product. So you have the sum of the elements conjugated times the elements of the other vector, which is, I think, the one that we all know. And what Schumacher did, so he basically also followed exactly Shannon's idea, just he replaced everything into the quantum set, and he considered the asymptotic setting, which means he took n IID copies, so identically and independently distributed copies of its initial state. So this is just a tensor product of each of the states in the specific systems. And what he does is he fed basically the state to an encoder. And in quantum theory, these encoders are general quantum operations, which are known as to be as completely positive trace preserving maps. But again, these are not important for my talk, but this is just a brief idea. And then this message is then stored in a space, which the aim is to have small dimension. And then this message is entered in a decoder. And in the end, we get something which is nicely approximated to our initial state. And again, Schumacher had a figure of merit where he measured basically how much the error is. But this is not, again, important. But what was important and what I want to use for my talk is the fact that Schumacher in 1995, he basically proved that the optimal rate at which we can compress information is basically given by the von Neumann entropy of the quantum state. So this is just the Schmidt decomposition of the state. So these are the eigenvalues and the corresponding orthonormal vectors. And von Neumann entropy I denote by S, and the von Neumann entropy of a density operator is just the negative trace of the product of the state with the logarithm of the state. So basically, if the rate of compression is greater than the entropy of the source, then there exists a coding scheme that can achieve a lossless data compression, and vice versa. So basically, from all this that I said, maybe I was a bit fast, but the only thing that we have to remember is that entropy functions, which are basically functions of the source that is fed to the encoder, are very important in data compression because they give the optimal rate. And what I want to do is I want to study properties of this function, basically. Okay, so in quantum information tasks, we usually distinguish two settings, as I mentioned earlier. So we have the asymptotic or the IID setting, where Schumacher compression, for example, falls into. And these settings are usually characterized, okay, except the asymptotic setting, we have also the single shot setting. And the difference between these two settings is that in the single shot setting, I consider only a copy of my quantum state, as opposite to the asymptotic, where I have many copies of my quantum state. And these two settings are characterized by different measures. So the IID setting is usually characterized by the von Neumann entropy and quantities that are directly related to it, such as relative entropy and mutual information. And the single shot setting is characterized by different quantities, which are known as Rayleigh divergences and smooth versions of it. But what we did with my supervisor is basically we asked the question whether we can find an alternative single shot characterization, which possibly includes an optimization over until a system for the IID settings. So basically, can I characterize tasks in the single shot setting by means of von Neumann entropy, for example? Okay, so that was more or less like the intuition upon which I will build basically my talk. And so my work was that you can find online is known under transcendental properties of entropy-constrained sets. And before I continue further on, I want to make a separation between semi-algebraic world and transcendental world, basically. So one thing that we learned in our algebra course, I remember this with Professor Chandrem, is algebraic numbers. So these are basically numbers which are roots of non-zero polynomials with rational coefficients, or equivalently with integer coefficients. And the typical examples are every integer, every rational, then square roots of numbers, etc. But every number which cannot be written basically as a root of a non-zero polynomial is known to be a transcendental number. And the usual suspects are e and pi, but in principle, it's very difficult to show that something is transcendental. So for example, it's known that these two numbers are transcendental, but it's not known whether their sum is a transcendental number. I mean, most probably it is, but as far as I know, no one has showed it yet. Okay, so except for numbers, we have such a separation between algebraic and transcendental worlds, also for functions and for sets. So basically, a function is known to be algebraic if its graph, at least locally, fulfills a polynomial equation. And if the function does not fulfill such a polynomial equation, it's known to be transcendental. And again, the usual suspects for transcendental functions are the logarithm, the exponential. And a function is known to be semi-algebraic if basically its graph will be a semi-algebraic set. What is a semi-algebraic set? So if I consider a set A as a subset of some real vector space, then this set is known to be semi-algebraic if I can write such a set as finite union of polynomial inequalities. So basically, semi comes in here because of the inequality sign in here. And every set which is not semi-algebraic is again called transcendental. Okay. So something else which was used for my work is also called Nash manifolds. So why do I use this? Basically, for every semi-algebraic set, there is the composition of these sets into Nash manifolds. And what are Nash manifolds? So these are basically manifolds that are at once smooth and algebraic. And the same goes for Nash maps. Basically, these are maps that are at once smooth and algebraic. You probably might wonder, how is this important in quantum information theory or just information theory? Well, basically, usually the distinction between the single shot setting, so the case where we only have one quantum state, and the asymptotic setting on the other hand, or like finite resources or infinite resources in quantum theory, well, this comes often hand in hand with the distinction between being semi-algebraic and being transcendental. And basically, this is the approach that I will also follow in my talk. But before I continue, I just want to mention some works which followed a similar path. There is a paper by Fannes, Nathaniel, and Werner in 1992, where they basically study the ground state of the antiferromagnetic spin, 1/2 Heisenberg chain, and they show that this cannot be a finitely correlated state because its energy, it's not algebraic, but it is transcendental number in the end. And another one, there is a note which was done by my supervisor, by Toby Cubitt and David Perez Garcia in 2011, where they talk about undecidability of problems in quantum information theory and how they attack this question. These questions are basically by checking decidability via quantifier elimination, or the very famous result in algebraic geometry, which is known under the name of Tarski-Seidenberg. So basically, this theorem says that if you have a set which is already semi-algebraic, so it can be written as finite polynomials, a finite number of polynomial inequalities and equalities, then basically having quantifiers upon this set, it will not change its semi-algebraic nature. And why do they use this? So many often use constraints in quantum theory. So basically for a matrix to be a density operator or evolutions, so in unitary operations, having a bounded norm or whatsoever. So these constraints are usually always written as polynomial equalities and inequalities. And the problem into talking about undecidability comes from an abstract point of view, basically from having to do quantifiers over infinite sets, because usually many problems in quantum theory, you have to take into account all decompositions from your states or all coding schemes or all resources, etc. And there Tarski-Seidenberg doesn't work, basically. Okay, so now that we have a feeling basically of what semi-algebraic is and what transcendental is, I will talk about the motivating example behind our work. So this is basically known as catalytic state transformations, and it was done by Wilming and co-authors. This was studied in depth in their paper, von Neumann entropy from unitarity. So what are these transformations? So basically, if you have a given initial state rho prime, and you want to transfer rho prime into a target state rho, then you can do this under the following rules. So basically, you are allowed to add a state to your initial state and then perform a global unitary. And basically, the final state, which I denote by rho 1, 2, might be correlated. And it's such that in one subsystem, you basically get your target state, at least up to a good approximation. And on the other subsystem, you get back your ancilla state, which in this case serves as a catalyst, basically, because it is returned untouched in the end. And the question is here, basically, that if you are given this initial state, what is the set of states which is reachable by rho prime? So basically, for rho prime, I denote by Sn the set of all reachable states in such a scenario, but I do add a constraint. So I'm adding the constraint that my catalyst is at most of size n, basically. And this is just a subset of a density operators set, basically. And what I do is I also define another set, which I denote by S. And this is just the set of states which have higher von Neumann entropy than the initial state. So basically in this paper, there was a conjecture which said that you can always characterize catalytic state transformation by saying that the von Neumann entropy of your target state is always greater than the von Neumann entropy of your initial state. And that's why we basically do such a separation and we try to study this. So a year later, a remarkable result by Wilming was that basically if you take the union over all these sets Sn, so if you do not impose a constraint on the dimension of the catalyst, then you will get the set of states that have higher von Neumann entropy than the initial state. So basically the limit of Sn, when there is no bound on your catalyst, will give you back S in the end. But we asked ourselves, basically, is there a finite n, which could be a dimension, a function of the dimension of your initial state, such that these two sets are equal. So basically, if I have, for example, a matrix, rho prime, which has dimension 3, do I really need a catalyst which has infinite dimension for me to make such a transformation? And how we tackle this question is basically the first observation that we have is that the set Sn is basically a semi-algebraic set. And this is courtesy of Tarski-Seidenberg theorem because everything defined here can be written as polynomial inequalities and the quantifiers basically do not change anything. And the second question would be whether the set S is semi-algebraic or transcendental. So basically, because von Neumann entropy in its definition has a logarithm, this smells very much transcendental. So if we manage to prove that such a set is transcendental, we basically are showing that these two sets are different, and we cannot bound the dimension of the catalyst basically by n or any number, which is a function of the dimension of the initial state. So now everything boils down basically to the question whether entropy-constrained sets, so basically the set S, is transcendental or not. In order to ask this question, we have to come with a criteria which discriminates between semi-algebraic sets and non-semi-algebraic sets. So if you notice, everything that is algebraic or semi-algebraic in my slides has a particular color, this orange color, and everything that is transcendental has a blue color. So maybe it's easier to remember these two notations by just distinguishing these two colors. So this theorem is basically built into two observations. So first, that algebraic functions have at most a finite number of branches, and two, if a level set is given by a differentiable function, then basically its normal space is particularly easy to access via the gradient of the function. And what we do next is basically we try to apply this theorem, especially the second part, and use the fact that the logarithm function has an infinite number of branches in order to get the contradiction that we need in order to show that the set S was basically not semi-algebraic. Okay, so back to our question. Another thing which we have to be careful is the dimension basically of the space that we work in. Because if we consider dimension 2, so if you're considering qubits basically, which are two-level systems, then these sets are very much algebraic, because basically the set of states that have fixed von Neumann entropy can be given also by purity of the state. So purity is basically measured by trace of the state squared. And this in the Bloch sphere basically is just this representation, and this is very much algebraic. So it can be written by polynomials. So the answer is that for dimension 2, entropy-constrained sets are semi-algebraic. This is not the case anymore when we go in dimension 3 and higher. And I decided not to present the proof exactly, but to give basically a sketch idea of how we proved this. Okay, so basically, this set here is the set of states that have fixed von Neumann entropy. And this can be proven to be a manifold, a smooth manifold. Next, since we are always proving things everywhere, what we do is we always intersect with an open subset of the set HD, which is just the set of Hermitian matrices of dimension D. So what I do, I take any state rho in my manifold, and I construct a diffeomorphism phi, which becomes an algebraic diffeomorphism when restricted to a sufficiently small neighborhood, basically. So I'm preserving the algebraic structure of my initial manifold here. And so I'm converting now basically all these matrices rho into vectors x. And this diffeomorphism is chosen such that the first d-1 components of my vector x are just the eigenvalues of my density operator. And for the rest, I don't really care. And why is this? So this is basically because entropy as a classical analog has Shannon entropy. And Shannon entropy is entirely dependent basically on the eigenvalues of your matrix. So as long as I know the eigenvalues, I'm fine, and I don't care what the other components are. Also because my manifold M is basically just the pre-image under C of the Shannon entropy, which means that if I consider the normal space at any point x, this would be just the span of my normal vector, And my normal vector is basically just given by the gradient of the function of Shannon entropy at this point. Okay, so I will work with the normal space because for me, it's much easier than to work with a manifold itself, basically. The normal space is just the space which is perpendicular to the tangent space at point X for the manifold M. Okay, next, what do we do? Is basically, so in parts of mathematics, assigning normal vector, which has unit norm, because I can normalize this, to any point of my manifold. So this assignment is also known under the map of Gauss map, basically. So I assign to every point of my manifold basically such a map. So I'm just assigning everything to the unit sphere, basically. And what I do next is I take a path. So this curve here in orange, I take a path, which is orange in purpose because this is an algebraic path, because I can get it by just intersecting with an algebraic surface, my manifold M, which I assume also to be algebraic. And I choose such a path such that I am basically fixing every component along this path except 3, because that is all the freedom I need in order to prove basically my statement. So now if I choose a component among this path, so a component which is not constant, and I compose this with a projector, basically, which is generated by this normal vector, and then I take the quotient of any 2 entries, diagonal entries of my projector, then in the end, I will get a function which involves the logarithm, and it's from R to R. Okay, now if I take this function and I put it in the complex plane, I can apply analytic continuation. And what I get in the end is I get these branches popping up, basically. So for algebraic functions, I still will have many branches, but these branches will end at some point. For example, square root of x, or third root of x, or whatever, all these end at some point. But the logarithm, we learned this also in our complex analysis course, that it has an infinite number of branches. And this is also known as having a non-compact Riemann surface, basically, which is never the case for algebraic functions. So these branches popping up is how the transcendental nature of the logarithm basically affects the level set of the entropy function. So if I summarize now this into the theorem, basically we show that for dimensions greater or equal than 3, and for any values of my entropy except the extremum, so except the value 0, which is for pure states, and the value ln of d, which it's achievable for something which is called Maxwell mixed state in quantum theory, but we don't have to worry about that. So the set of d by d density operators that have fixed von Neumann entropy is nowhere semi-algebraic. And we, as 2 remarks for this theorem, is basically that we proved this theorem for the logarithmic base e, but this can be proven basically for any logarithmic base, because if I change the base of the logarithm, it means that I'm just changing the value of c. And this doesn't affect anyhow the proof that I just presented. Because many people are worried when I say about e, because they say, okay, we are measuring bits or qubits, so why you do not use 2? But for me, it was easier to use e, but it's the same if I use any other base, basically. And the same results also hold true for any inequality here instead of equals c, because of properties of semi-algebraic sets, basically. That the boundary of a semi-algebraic sets remains, again, semi-algebraic. Okay, once I had this theorem, then we thought, okay, can we say something if I add another constraint to this set, basically? So this part here, so these 3 conditions mean that my matrix rho is a density operator, and this was the part where I say that I have a fixed von Neumann entropy. But we thought, okay, can we say something else if we add basically another constraint to our set? And it turns out that we can say more stuff, basically. So Adding additional constraint to that set in quantum theory means that we can consider the energy of the state, we can check the expectation value for any observable, we can check the distance of the state to a specific target, whatever. But the thing is, we have to be careful when we put these things in a mathematical form, because basically how we express this is we always express them using differentiable function from the set of positive definite matrices to the real line. Okay, so once we have this, we can prove also the following theorem, which has basically the same conditions, except that now I add a second value C2 here, which can be anything in R, and my function is continuously differentiable. And I can again say that this set is nowhere semi-algebraic in any neighborhood, basically. It's not semi-algebraic in any neighborhood of rho. And this condition here for the commutator of rho and the gradient of H at rho, it just says that the spectrum of rho does not entirely depend on H rho, basically, which is good because we no more have only entropy, but we have other functions which depend on more entries of your matrix rather than just the eigenvalues, basically. And why did we do this? So when we formulated this theorem, we had a specific thing in mind, because we wanted to talk about basically the level set of the relative entropy. So relative entropy is again defined like this. So now I have two density matrices I consider are rho and sigma, and this is defined as long as the support of rho is contained in the support of sigma and it's infinity otherwise. So basically, again, similarly, applying the first theorem that I mentioned, we can prove that such sets are not semi-algebraic in the space of permission matrices unless this set is empty. So basically, you can notice here that I am fixing the density matrix sigma. So this is arbitrary, but it's fixed. And I'm basically only working with a set of states rho, basically. And we thought whether we can say something similar, basically, also when we just change roles for rho and sigma. So we fix rho and we vary sigma. And it turns out that basically we can say again the same thing. So we can prove again that these sets are nowhere semi-algebraic, basically. So I didn't present a proof for this because this is work in progress and it will be very soon on arXiv. But I just wanted to mention that we can do more than this, basically. And we also studied the case where both of them are free. So both rho and sigma vary. And we also can say the same thing then, that these sets are not semi-algebraic, basically, in HD, unless, again, the set is empty. And we care for these things because these entropy quantities usually characterize many information tasks in quantum information theory. And it's nice to know these properties because then it's easier to characterize different transformations, basically. We also are considering other entropy functions like Rayleigh entropies, for example. But again, that will be very soon on the next paper, which will be published, I guess, rather soon because it's almost done. And as a takeaway from this talk, so the first message that we learned is basically that the set of states that has higher von Neumann entropy than your initial state that you consider, it's not equal with the set of catalytic transformations when you impose a constraint on the dimension of your catalyst, basically. So another message is, I think this is more important actually, that you can make a separation between the single shot setting and the asymptotic settings in quantum theory or finite and infinite resources by just distinguishing between semi-algebraic world and the transcendental world. As a no-go result is basically that single shot characterization of information theoretic quantities such as von Neumann entropy, mutual information, relative entropy, and so on, is never possible basically if you try to bound the dimension of your catalyst by default. So unless you're considering unbounded catalysts, you can do such characterization by these entropy measures. And as I mentioned earlier, we believe, and we almost finished the proof, that the variance of the presented argument do apply also to other entropy quantities by just revealing their semi-algebraic or transcendental character. And this is work in progress with Chokri Manai, which is a PhD student also in one of the groups here in Munich. And I think with this, I end my talk. And I thank you for your attention. And I hope you have questions for me.
Thank you very much, Vjosa. That was a great talk. So now I ask our audience, does anyone, I saw some raised, I think you're, okay. Vjosa, you can see somebody raise their hands, right? Or no?
No.
Sorry, okay.
I didn't see anyone while I was presenting, actually, but.
All right. All right, so I've become the host again. So any questions?
I hope I wasn't too fast.
Well, it was a bit, but that's fine. So let me break the ice then. Let me ask a question myself. So you mentioned the semi-algebraic functions as well, not just the sets. And then in the results, you had results about the sets. Do you consider also the functions and their graphs? So what happens in that case?
So basically, how we prove this theorem for these level sets of the entropy, so for this manifold, is we consider algebraic functions in there. So this function f, which I said is a composition of this path and the projector, that is basically an algebraic function.
Okay.
So I use there the fact that this is an algebraic function. Because if I have an algebraic and analytic function, then I can apply these continuation to the Riemann surfaces, basically.
Okay. And then going back to, I think it was theorem 2 or something like that. So you had some very specific, so it's no longer in front of me, but some very specific result regarding specific manifolds. Like there was a projection. Could you go back to theorem 2, please? Or is that
yes, I cannot share my screen, but I can go to theorem 2.
I think you can share it now.
Yeah. So the theorem 2, okay. So this is theorem 2.
Yes.
So here, sorry, here you're talking about, so this projection, you mean this?
Okay, theorem 1 actually, yes. So so you have a Nash submanifold and you have an orthogonal projector.
This can be shown, so we do show that this orthogonal projector is actually also a Nash map. And we do this, so this is exactly how we use algebraic functions. So we have all these Nash maps, their composition remains a Nash map, and then we use this first part that if F is analytic and algebraic over R, yes, if it is defined from I, this I is a subset, is an open interval of R to R, basically, yes. When we create this criteria is that we already had half the proof actually for von Neumann entropy. And there we wanted to stick with this normal space, which is basically the gradient of the entropy. That's why we introduced the projector in the first theorem.
Okay, and the H here can be any function?
Yes, any function. In our theorem, H is just the ratio of any two entries of the projector when it's composed with a path in my manifold. Okay,
great. So and so what's your next project now? What is this going to lead to?
So basically there are some quantum information tasks which basically, so there are some characterization between states, and these characterizations are fully determined by just saying, for example, that the entropy of a pair of states is bigger or equal to the entropy of some pair of states. And usually, always these transformations are very much semi-algebraic, I would say, unless you consider infinite dimensions for ancillary spaces, basically, or you have an unbounded protocol. So you share and receive information many, many times. You don't bound this. So basically everything is semi-algebraic unless you have these specific scenarios. And then these are always, or maybe I shouldn't say always, quite often characterized by entropy measures. So I think it's quite important if we would know by default whether these entropy measures give rise to semi-algebraic level set or transcendental. Because knowing this, you can actually say something about the transformations in hand that you have. And so I think for us, So for us, it was very, sorry, it was difficult to prove that von Neumann entropy basically has a transcendental level set, because then many other entropy quantities build up upon that one. So if you know the proof for that one, I think then it's way easier to say something about the other entropy quantities.
Okay, so does anyone else have a question or comment? Okay, so nëse ka askush pyetje ose komente, atëherë le ta falenderojmë Vjosën. Faleminderit shumë Vjosa për prezantimin edhe për hyrjen në këtë fushë të rëndësishme edhe interesante. Shpresoj që ka pëlqyer edhe kolegëve, edhe për ndryshe shihemi Prishtinë.
Qëndrim, a moj me një pyetje shpejt, a shqip ose anglisht?
Go ahead.
Okay, so yeah, my question is quite general. So what I remember reading about information theory is that it's defined in very probabilistic terms, so referring to the original work of Shannon. And I actually read kind of late into the seminar, so I missed the early part. And I also want to say that quantizing objects is a kind of a common theme in algebra. So my question, and from what I saw from your talk, it seems that it's a very kind of algebraic treatment. So my question is, when you look at this quantum information theory, do you still retain the probabilistic ideas that are there when you define information theory?
Yes, completely. So basically, probabilities sum up to 1, and then this is the trace condition, basically, that you have for density operators. So basically, the quantum idea entirely saves everything which was in the classical information theory. I think one of the smallest difference is the fact that in quantum theory happens something which is known as entanglement, and this does not happen in classical theory. This entanglement means that if you have a state which has many copies, basically you cannot change anything for any of these copies without actually altering also the other copies, even if they are very, very far away from one another.
I see. Thank you very much.
Sure.
Great. Any other questions? I think this is it. Vjosa, faleminderit shumë.
Faleminderit juve.
Faleminderit edhe Hamdiu për faleminderit.
Shkemi Hamdi.
Faleminderit shumë. Shihemi Vjosa herë në ardhshme kur të jeni në Kosovë.